Oh. Good evening, everyone. Welcome to the Bioreactor Design and Analysis tutorial week 4. So I will be discussing few problems. Please join with me along solving the problems. So my voice has gone bad due to fever, so I will not be talking more. I will wait for a few minutes and we will start solving the problems. So let's start solving the problem. So this is the first question where Cymomonas mobile cells are used for the chemostat culture for the production of ethanol. The feed contains 12 gram per liter of glucose and all other details are mentioned below. I will give 2 minutes to read the question and then we will start solving the problem. So let's start solving the problem. So the question A is what flow rate is required for a steady state substrate concentration of 1.5 gram per liter, and your steady state substrate concentration is given. From this we can back calculate our flow rate. With this flow rate we will be calculating the question B and C. So let's start the problem. So let's substitute the values of mu m, s, ks, and then we can calculate D. That will be 0.64 R inverse. So we have calculated the value of mu, which is equal to d at steady state. So we all know that uh, so we all know that d is equal to f by v. So f by v means what is we have to find this one. In the given value, what is the volume? It is 60 meter cube fermented. So D we know, which is 0.264. R inverse equal to F divided by 60 meter cube. If we do this, we go here. So 0.264 into 60 will give our F value, which is what? It's around 15.84 meter cube per hour. This is your flow rate. Now, we have found our flow rate, which is around 15.8 meter cube per hour. With this flow rate, we have to calculate cell density. So cell density, when the synthesis of the product, which is ethanol here, is coupled with the energy metabolism, then the formula for such case would be x equal to d into Si minus S divided by d y-axis plus ms. Note that here mu is equal to d, so that's why I have replaced the term. Instead of mu, I have used d. So just we know all the terms. It's already given there in the question. So just we have to substitute things. So this is 0.264 to SA is 12 minus 1.5. Is it correct? SA is 12 and S is 1.5. Y-axis is how much? 0.06 and MS is 2.2. Let's substitute this. And solve. So the cell density is around 0.42 grams per liter. So let's go on to the next part of the question. This is at the flow rate, which this we found out to be 0.42 gram per liter. So the part C of the question is at the flow rate of E, which is 15.8 meter cube per hour, what concentration of ethanol is produced? So our ethanol is the product. So assuming our ethanol is not present in the feed, if we assume that not present in the initial stage, feeding stream, if we assume this, PI means product at the initial stage is 0. So then the steady state product concentration can be calculated by P is equal to, this is the uh, product mass balance only, Pi plus QPX divided by D. So can substitute Pi is equal to 0 because in the initial phase product is not there. So QP value we are substituting 3.4 into, we have calculated the X value which was 0.42 gram per liter, divided by D is also calculated, which is 0.26. We do the calculation for this. It is around 5.40 grams per liter. So this is the steady state concentration of the product. Um, so this is a simplest sum in case of continuous reactors. So we'll go to the next question. I'll give you 2 minutes to read the question. Uh, if anybody, this is very similar to your assignment of week 4 questions. I know you guys would have solved. So please join with me along to solve this problem. I'll give you 2 minutes to read the question. Then we will start solving the problem. Start writing down our given values. So by looking at the diagram, know it is a chemostat. Chemostat is your continuous cultures. So let's read the problem out. We will write down the given values. So the feed flow rate is 100 liter per hour. Volume is 1000 liter. It is your glucose is the limiting substrate. Sterile inlet feed means inlet feed is your S naught. You can look at the diagram to name the what exactly it is. So S naught is 10 gram per liter. So your mu max is, sorry, here it is mu. Mu max is 0.4 R inverse. Ks is 1.5 gram per liter. And Yx is, sorry, is 0.5 gram per gram. And our recycle stream flow rate, so that's all. One more thing is, um, it has been used in this reactor system with the biomass concentration 4 times as large as that of the existing from the reactor. Our concentration factor C is equal to 4 times greater than that. So the first question is, what is the recycle ratio alpha for the system? Let's start solving that. So alpha is given by flow rate in the recycle stream. Okay, wait a second. Divided by flow rate to the vessel or reactor, which is, so this would be, so here recycle stream flow rate, which is FR, is equal to 10 liter per hour. Which is, so we can do 10 liter per hour divided by the flow rate is 100 liter per hour is equal to 0.1. So alpha is equal to 0.1. So what is the next question? Determine the net specific growth rate for the system in terms of R inverse. Mu net, mu net has to be calculated. If we have solved the assignment problems and listen to the lecture, you will understand the formula. Mu net is equal to D 1 plus alpha minus alpha C. So we just have to substitute the values. For this, we need the value of D value. So D is nothing but F by V. F is what? Don't confuse with 10 liter. The F is flow rate to the vessel, which is 100 divided by volume, which will give you 0.1 R inverse. So substitute it back here. Unit will be 0.1. 1 plus alpha is what? 0.1 minus, again alpha is 0.1 into C value is 4, because it's mentioned in the question that the biomass concentration is 4 times as large as that of the existent from the reactor. So your concentration factor C is equal to 4. So if we solve this, you'll get the value for mu net. So that would give you 0.07 R in this. So what is the part C? Determine the substrate concentration inside the reactor at steady state. Means how much substrate is inside the reactor during the time of steady state. You have given your S naught is 10 gram per liter and how much is remaining inside at the time of steady state. So to calculate this, We will do write the substrate in terms of at steady state. Substrate concentration is equal to but here this D will be replaced in terms of 1 plus alpha minus alpha C as it is a recycled reactor. Should be careful with the formulas because in terms of recycle this D will be replaced by D is equal to 1 plus alpha minus alpha C. So let's substitute the values of Ks, alpha, alpha C, everything. We do this. What would be the answer? Can anybody um, write down the answer in the comment section? Yes, Ajay, it is correct. It is around 0.31 gram per liter. So let's go to the. Thanks for the answer, Ajay. So let's move to the B portion of this question. So we have to determine the concentration of the biomass inside the reactor at steady state. So to calculate the concentration of biomass inside the reactor, what would be the formula? It will be similar to your uh, batch formulas only. So case of cell concentration Ax is equal to y-axis into your S naught minus SF divided by this would be 0.5. It's not as 10 and RSF is 0.318. So this is the cell concentration at the time of steady state. So, so the last part of the question is determine the concentration of biomass at the recycle stream. So from here you are taking your cells out, separating the cells, then taking it back in. So in the recycle stream, the cells would be what Cx1. So we just have to multiply by the concentration of the cells into the concentration factor. If we do that, Cx1 equal to 4 into your concentration cells 27.8. So this would be the cells in the concentration, which is cells in the recycle stream after separation. So this is all about the second question. So this is the two-stage hemostat question, which is similar to your assignment question. Um, I hope you have already submitted the question assignments. I'll give you a few minutes to read the question. Note down the given in your note papers. Then we will start solving uh, each part of the question. Please read the question. We will start solving after 2 minutes. Shall we start solving this question? So, what is a two-stage hemostasis for the production of secondary metabolites? The volume of each reactor is 0.5 meter cube. The flow rate of the feed is 50 liter per hour. Mycelial growth occurs in the first reactor. The second reactor is used for product synthesis. So it is a two-stage where your product is grown in one reactor, and the cells will be transferred to the next reactor to synthesize the product. Um, the concentration of the substrate feed is 10 gram per liter. Kinetic and yield parameters are given here. You can note down the given values. So here it is given that we have to assume the product synthesis is negligible in the first reactor and the growth is negligible in the second reactor. So here product is negligible means your P will be 0 here, and there in the second reactor it is given your growth is negligible. So with this given statements, we have to determine the cell and the substrate concentration entering the second reactor. So by if you can see in the schematics, we have to calculate the cell and the substrate concentration, which is X1 and S1. That is what is entering the second reactor. And overall substrate conversion, how much substrate is being converted in the two-stage system, and what is the concentration of our final product. So let's start solving the problem. Uh, Always take some time in reading the question, understand it first, and then start solving the problems. Otherwise, in midway, we will be confused. So now, let's start solving the problem. So always keep same unit in your when you are following the problem. So here, I think it is all in kilogram meter cube and kilograms. So let's convert whatever in grams to kilogram per meter cube. It will be helpful. First, if we convert the data means it will be easy for us. So, so our inlet substrate concentration, let us keep that as SI, is 10 gram per liter. So if we convert to kilogram per meter cube, it will be what? Around, it is the same, right? 10 kilogram per meter cube. Because 1 meter cube is 1000 liters and 1 kg is 1000 grams. 1000 will get cancelled. It will be 10 kilogram per meter cube. So we should take into consideration that dilution rate will be the same for both the reactors, and this can be calculated by using T is equal to F by V. The volume of both the reactors are also same, which is 0.5 meter cube, right? So the flow rate is 50 liter per hour. If we convert liter to meter cube, 1 meter cube is equal to 1000 liters, so we will multiply by 10 to the power minus 0.5 meter cube. What will be the answer? Point 1 R inverse is 0.1 R inverse. So what we have to find is the substrate and the cell concentration. So the cell and the substrate concentration which is entering the second reactor are the same as that in your first reactor, which is leaving from the first reactor is going to be the same as that entering the second reactor. They both are the same terms, right? So we can calculate the substrate concentration by using the formula which we always use. This is S equal to dks case of steady state mu minus d. So now we know all these values, it's already given. We are just going to substitute. So d is 0.1 R inverse and Ks is 1 kg per meter cube. Your mu is 0.12 R inverse minus your d, which is 0.1 R inverse. So what would be the value of S? So it will be around 5, right? Approximately 5 grams per meter cube. So the value of S we have calculated. So how do we calculate our X term? A formula which is similar to the previous problem, which is X is equal to D is I minus S divided by D divided by Y xs plus ms. Substitute the noun variables there. 0.1 S value we just found out. So what would be the answer for X? Around 2.22 gram per meter cube. So this is the concentration of your X. So let's go back to the question. So for the answer is equal to 5 kilogram per meter cube. X is equal to 2.2 kilogram per meter cube. This is the cell and the substrate concentration which is entering the second reactor. So now we have to calculate how much of substrate has been converted, which is the overall substrate conversion we have to calculate. So for that, what we will take into consideration. So we know that the growth is not there. Just given as the growth is negligible in the second reactor. So we will keep the growth as the same growth which is entering in, which is the X. Same X means this 2.22 kilogram per meter cube. So if we do the mass balance around the substrate, is what mass plus P divided by YP plus MS X into V is equal to 0, right? So, what are the terms we'll get 0 here? So here it is the steady state limiting substrate. is the glucose, right? This term will go. We have to rearrange things. Equal to QP divided by YPS. So we can substitute the values which we know to find the unknown values. So here the unknown is S. The inlet of the second reactor would be 5, right? We have calculated. This will go here. Means 2.2, which is we found out concentration of the cell. And then only we will know how much has been converted. This term is to convert to meter cube. So now let's solve this and get the answer. Can anybody solve this answer? Get the answer for this? What would be the answer? It's around 0.308 something, right? Approximately 0.3 kilogram per meter cube. So if we calculate as this is the substrate in the now remaining of the second reactor. So if we if we take overall substrate conversion, your first reactor means your initial was 10 gram per liter. At the end, which is at the end, when the reactor when it reaches the second reactor, it would have converted to 0.31. So now we can calculate the overall substrate conversion. So 10 minus 0.31 divided by your initial into 100. So it will be 97, right? So 97% of your substrate has been entirely converted in your second reactor. The overall conversion is 97%. So, what is the question C is? What is the final concentration of the product? So, for this, we have to start from our product balance. So, here it is clearly mentioned that your product is not formed in the first reactor. So, we can keep your, so in case of C, FBI, the product concentration we are doing by mass balance at steady state, if it equal to 0. Here this term becomes 0 because inlet in your first reactor product is not going to be there. It is given. Here it is. So we can rearrange the terms. Rearrange it. Fp is equal to Qp is equal to Qpxv divided by F. So substitute the values of P, X and V, F here. What would be the answer? So what would be the answer? Please calculate and um, put it in the message box. What is the answer? Nobody solved. Let me check the answer. The answer is 3.52 kilogram per meter cube, right? So this is the third question. So I'll move on to, does anybody have any doubts in the three questions we have solved? Okay, we'll wait for another 2 minutes and then start the question fourth. That would be the last question. The fourth, so this is the fourth question. It is a chemostat with three cycle, similar to your second problem. Um, so please go through the question for 2-3 minutes. Then we'll start solving the problem. In the meantime, if you have any doubts regarding the previously solved three problems, you can ask in the message box. So let's start the first problem.
Yes, ma'am.
Yeah. So we'll just note down your given values. Your that is a chemostat with recycle, and your feed flow rate is 100 ml, and your volume is 1000 ml. Your YM of X 0.5 gram of dry weight process of your substrate, and S naught is 10 gram per liter. Mu is 0.2, K is 1, C value is 1.5, and alpha is also given, which is 0.7. It is also given your system is at steady state, and also you know that it is a chemostat. This schematic is for your reference. So what we were asked is, in your question A, we were asked to find the substrate concentration in the recycle stream S. So in this recycle, how much substrate concentration will be there? So to calculate this, what you will be doing, you have to first start writing the mass balance for the chemostat with recycle, which is Fx naught plus alpha SCX1 minus of 1 plus alpha x1 plus v into mu net x1 v into dx1 divided by dt. So this is, if you remember, this is your how you will start writing your mass balance for hemostat with recycle. So if we do know that it is steady state, so if that is the case, dx by dt should be 0, considering it is a sterile feed. Then at also at steady state, your mu net will become 1 plus alpha minus alpha c into d, right? So this mu net is needed for you to calculate your substrate concentration in your X stream, which is recycle stream. So first we will calculate the mu net, substitute this mu net in your the formula, right? Minus mu net. So how do we write your mu net? What is the alpha value is 0.7, right? 1 plus 0.7 minus 0.7 into 1.5. What's the D? Is the dilution rate given? We have to calculate it. It is F by V, right? So F is 100 and V is 1000, which would be 0.1. Okay. So if you do this, what would be the answer of your mu net? It would be 0.065 R inverse. So this is your mu net value. So you found the mu net value. From this, you can substitute here. That would be S is equal to Ks is what, 1, right? So mu net is divided by 0.2 is your mu max, 0.065. What is the value of S then? It is 0.47 gram per liter. So we just found the substrate concentration in the recycle stream we found. We also found the specific growth rate. CSR rate is mu net. The organism is also found. So we solved A and B together. So the next would be find the cell or biomass concentration in the recycle stream. This is the recycle stream, right? So you need to calculate x1. So to calculate x1, how do you do? Then equal to your dilution rate S naught minus S. The 0.1 into 10 minus substrate we just calculated 0.47 into your y excess divided by 0.065. Point 0.4765 divided by around 7.33 gram per liter. So this is your this is the cell concentration in the recycle stream, which is x1. So now you know the x1. Find the cell concentration in the centrifuge effluent. So in case of recycle, you will be taking your some portion of your media, allow the cells out, separate the cells that will go out. This is cell separator or centrifuge. The remaining media along with a little bit of cells will be going inside. That is what you could just calculate, which is x1. And what is going out of the centrifuge or cell separator is the x2. So to calculate that, you have to do a mass balance around the concentration yields. This 1 plus alpha of x1 equal to alpha c x1 plus x2. How did this come? So this 1 plus alpha into x1 u alpha c x1 this. Sorry. You can write this question. Can do a mass balance around the concentration 1 plus alpha into x1 is being taken out. Simple mass and mass out balance only. Alpha into c into x1 plus x2. If we do this, rearrange the stuff. So just substitute now 1 plus 0.7 into how much x1 value we calculated? 7.33, right? 7.33 minus alpha is 0.7 into c value is 1.5 into x1 is how much it was? 1.3. So this what would be the answer? 4.71 grams per liter. So this would be the concentration of cells in the centrifuge exploit. So, have any doubts in the problem solved today? Can ask in the message section. Do you have any doubts? Do you want me to repeat any problem? Please let me know in the inbox. No doubts to anyone? So if you don't have any doubts, you can leave the session. Do have any doubts, you can stay back. And if there is any doubts regarding the live session, please ask in the discussion forum, mentioning it is from the live session. So we have got the unit is equal to d plus alpha minus alpha c. Now if we substitute, this is how we got. So now if we substitute the values given, we will be able to solve the part A and B of the problem. So solving the 16.7 0.065 it is 0.065 R. Substitute we can calculate. Now we got the substrate concentration. What was asked? Substrate it is specific growth rate of sorry, this is unit of the organism is found. So now it will be the cell biomass concentration in the recycle stream, which is x1, and the cell concentration in the centrifuge extract. So these two only we have to calculate. Let's That's all I hope. I have covered on the some tutorial problems. So this question is new unit. Sorry. Uh, we have solved four problems on chemostat, two with continuous cultivation chemostat, and two with the chemostat, one with the chemostat with recycle, and the other one is a two-state chemostat system. So I hope there are no questions. Uh, if you have any questions, please uh, make me to my previous mail ID given, or if you have any other further doubts, you can uh, bring in discussion forum. Mention in that it is from live session of Friday, so that I will be able to clear your doubts at the earliest. Thank you for joining.